Good evening, everyone. My name is Sean Simpson, and I'd like to welcome you back to another Tech Talk in our series sponsored by Remake Labs. Today, we have the pleasure of welcoming Lillian Ten to give us a brief talk about message brokers. So without further ado, I'll pass it on over to you, Lillian.
Thanks, Sean, for this warm introduction, and special thanks to Remake Labs for sponsoring this Tech Talk. Good evening, everyone. My name is Lillian, and I am here tonight to talk to you about message brokers. Before we start, here's a brief overview of what we're going to cover. We will define what a message broker is, go over a brief history of how message brokers came to be. We will also discuss the structure of message broker, as well as the pros and cons of integrating it in your project. We will also mention some of the most popular message broker systems. So, what is a message broker? A message broker is a software system that facilitates the exchange of messages between different applications, services, or components within a distributed system. It acts as intermediary that receives messages from a producer and delivers them to consumers based on predefined routing rules and message patterns. Message broker serves as a collaborative integration tool to support architectures such as cloud-native, serverless, microservice-oriented, and hybrid cloud setups. Well, now when we establish what message broker means, let's look into what message broker actually is, why they came to be, and how they work. The journey of message brokers goes back to the early days of computer networks. Initially, applications communicated directly with each other using their own rules and methods. While this worked for smaller setups, it became messy as networks grew bigger and more complicated. Middleware was introduced to tackle this issue. It acted like a mediator, helping different systems understand each other's language and communicate smoothly. One of the earliest examples of middleware was remote procedure calls, or RPC, which allowed applications to call functions on remote systems as if they were local. Then came messaging systems, designed specifically for sending messages between applications. They introduced concepts like message queues and topics, making communication more reliable and organized. IBM's MQ series was introduced in 1992 and became one of the pioneering messaging systems. As businesses expanded, they needed better ways for their systems to talk to each other. This led to a surge in demand for messaging systems that could handle large-scale communication. Messaging systems started offering features like guaranteed message delivery, message persistence, and also support for different message formats. To make messaging systems work seamlessly together, experts worked on creating common rules and standards. This ensured that different systems could understand each other's messages. The Java Message Service, or JMS API, was introduced in 2002, and the Advanced Message Queuing Protocol, or AMQP, was developed in 2006. Today, message brokers have evolved to support modern technologies like cloud computing and microservices. Message brokers also integrated in cloud platforms like AWS and Google Cloud. So how do message brokers work? Before we start, let's go through some basic concepts of a message broker. A producer is an application that dispatches messages. In the publish-subscribe pattern, which we will discuss shortly, they are referred to as publishers. A consumer is the endpoint that retrieves messages from broker. In the publish-subscribe pattern, they are referred to as subscribers. In order to consume a message, a consumer has to be registered to a queue. So, what is a queue? A queue or topic is a data structure serving as a temporary storage buffer for messages until they are ready to be retrieved by the consumer. A queue follows a first-in, first-out pattern. As we see from this diagram, the message broker receives and potentially converts messages from the producer. Then it arranges and retains them in a message queue until they are picked up by the consumer. There are two most common distribution patterns for message brokers, point-to-point messaging and publish-subscribe pattern, also known as pub-sub. In a point-to-point model, messages are sent from a single producer to a specific consumer. Each message has only one consumer, ensuring that it is processed by exactly one recipient. Messages are typically delivered to a queue where they await processing by the designated consumer. Once a message is consumed, it is removed from the queue, ensuring that each message is processed only once. In the point-to-point model, the message sent to only one consumer, even if many consumers are listening in the same message queue. This model is well suited for scenarios like where messages need to be reliably delivered to a single recipient without being shared or broadcasted to multiple consumers. There are two types of point-to-point messaging, fire and forget, and request reply. The difference between those is how the message sender cares about the status of the sent message. In fire and forget model, the producer sends a message to a designated queue and does not wait for any confirmation or response from the consumer. An example of this would be an application that may log events without waiting for confirmation that the log messages have been processed. In the request reply model, the producer sends a message to one queue, and then it waits for the response from the consumer. An example of this would be in some financial operations, where you want to make sure that the transaction was processed only once. In the publish-subscribe messaging pattern, often referred to as pub-sub, the message producer, called publisher, pushes a message to a specific topic, and multiple consumers, called subscribers, subscribe to that topic they're interested in. All messages published to a topic are delivered to every application subscribed to that topic. This method resembles broadcasting, establishing a one-to-many relationship between the sender and its recipients. An example of this would be an airline. If the airline were to broadcast updates regarding the flight landing times or delays, this information can be useful to various parties, such as ground crews, flight attendants, pilots, and of course, passengers. There are more variations to this pattern. You can have multiple subscribers attached to one topic, or you can specify the criteria for retrieving only desirable types of messages. So now let's go over some advantages and disadvantages of message broker systems. The first one would be message brokers enable the separation of system components, allowing them to communicate independently through messages. This decoupling mechanism enhances system flexibility and allows components to evolve and operate without directly impacting one another. In the event of a failure, message brokers redeliver the messages. If the messages remain undelivered after numerous attempts, the messages are rerouted back to the producer. Message brokers provide asynchronous communication between services. This means that the producer doesn't have to wait for the response from the receiving service. The producer and consumer can exchange messages regardless whether the other one is online. A message broker will deliver the message whenever the consumer becomes active. As the number of services and applications grow, the complexity of managing multiple message brokers also increases. As complex system will require careful configuration and management, this will increase debugging time and also troubleshooting time. There can be a substantial learning curve since message brokers are so complex, and they require setup and a lot of management. Message brokers will most likely be used to store and transmit sensitive data, which makes them a potential target for attackers. Some of the most popular message broker systems are Apache Kafka, RabbitMQ, Redis, Nets, Memphis Dev, Amazon SNS, and Amazon SQS. Kafka is an open source messaging system. It was developed in 2011 by LinkedIn engineers who faced the problem of integrating huge amounts of data from their infrastructure into a Lambda architecture. Kafka was later acquired by Apache Foundation. RabbitMQ is an open source message broker software that was developed by Rabbit Technologies in 2007. There are, of course, some difference between those two services, but we will go over some of them. And the first one is the messaging model. Kafka stores messages in topics, which are great for handling large volumes of data with high throughput. RabbitMQ, on the other hand, uses queues to store messages. It is more suitable for traditional messaging scenarios like task distribution. Kafka persists messages to a disk, which is ideal for scenarios requiring long-term storage. RabbitMQ, on the other hand, supports message persistence, but doesn't store messages to a disk by default. In terms of scalability, Kafka effectively scales horizontally across clusters, which is very useful for handling big data and high loads. RabbitMQ, on the other hand, can be clustered for high availability, but it also has some limitations in scalability compared to Kafka. In terms of message semantics, Kafka guarantees at least once message delivery. This ensures that messages aren't lost. However, there's a possibility that the messages may be duplicated. RabbitMQ, on the other hand, offers flexibility in delivery modes, allowing developers to choose between different message delivery semantics. Also, RabbitMQ is built on Erlang, which means that it can benefit from its lightweight processes, making it more efficient in handling multiple tasks at once. In summary, Kafka is preferred for handling big data and real-time processing, while RabbitMQ is better suited for traditional messaging needs. Well, I hope this tech talk has provided some valuable insights on message brokers, and here's my works cited. And now I would like to open the floor for questions. Well, since there are no questions right now, here's my contact information, and please feel free to reach out anytime. I would like to thank everyone again for joining in this evening, and special thanks to Remake Labs for sponsoring this tech talk. Back to you, Sean.
Thank you, Lillian, for that informative talk, and thank you everyone for coming out tonight. We'll see you at the next one.